Here a supply voltage E and series RC with switch S closed at time 0. When switch is closed, current flows and capacitor charges up. By KBL, the voltage is equals to the BR plus BC, and that is the supply voltage, equals to the supply voltage. Our BR is I times R given by the equation I times R, and the BC is given by the equation charge divided by the capacitance C. Then expressing the equation in terms of the current and charge, we have here IR plus Q over C equals to E. But we need to express the equation in terms of Q and transform the equation into a differential equation. The current I is expressed as a change of the rate of change of charge per unit time. Then expressing the equation in terms of Q, then this is our differential equation, and this differential equation is a linear differential equation, and the solution may be determined using different methods. But in our approach, as we have discussed last meeting, we shall approach this using the steady state component and the transient component. The transient component is derived from the differential equation equated to 0, and then roots are determined. And from the roots, we can now determine what would be the solution for this differential equation. And for this differential equation, the roots is real, so therefore the solution is the transient component is equals to the Ke to the negative T over Rc. The K is an arbitrary constant which shall be determined by applying initial conditions. For the steady state component of the charge, the charge in the capacitor changes and it will approach to the equal to the supply voltage. So therefore, the E is the final value for the charge in the capacitor. Since it is the final value of the charge of the capacitor multiplied with the capacitance, that would be the final value of the charge stored in the capacitor, which is the steady state value. Then steady state value plus the transient component of the charge is equals to the complete solution for the differential equation, or it is the charge stored in the capacitor at any time t. This is the complete solution. However, we need to determine the value for K by considering initial conditions, such as in case 1, at time 0, the charge stored in the capacitor is 0, meaning there's no initial charge in the capacitor. Substituting the values in the equation, the charge at time 0 is 0 is equals to EC plus K. E to the 0, since time is 0, this is equals to 1. So therefore, the K of the equation is equals to negative EC. Substituting this K to the equation of the charge at any time t, we shall have the equation for the charge at any time t. And factoring out easy, we can have the final form for the charge stored in the capacitor at any time t. And as you can see, this is almost the same form with the current behavior in a series RL. However, this is not a current, it is a behavior of the charge. So this is a behavior of the charge in the charging of a capacitor. In case 2, if there is a in case 2, at time 0, the charge stored in the capacitor is equals to Q sub O, and this is could be positive or negative depending on how it is connected in the circuit. Substituting the given condition in the equation, this will give us the arbitrary constant K as equals to Q sub O minus EC. Rewriting the equation, the Q as a function of time would become EC plus Q sub O minus EC. This quantity is multiplied to the e to the negative TRC. If I'm going to separate the Q sub O in the equation and form again the EC together, and this is EC times 1 minus e to the negative TRC is a condition exists when Q sub O is 0. This is the case 1. Now, when Q sub O is exists, there is additional value for charge that adds up or subtracts to the charge due to the supply. This is the charge due to the supply. This is Q due to E, and this is the Q due to the existence of the Q sub O. So when Q sub O is 0, so what you consider is just the EC times the quantity of 1 minus e to the negative t over RC. When Q sub O exists, then you add this Q sub O e to the negative t over RC, which is a decaying form of charge stored in the capacitor. If we are going to plot this behavior for the response of the capacitor in the circuit, the charge without Q sub O is that the charge approaches to its maximum value, which is steady state, value, which is equals to the product of the voltage supply and the capacitor in the circuit. While the existence of Q sub O, which is considered, let us consider it to be positive, this Q sub O decays, decays as the time elapses. And if this is positive, the Q sub O initial at time 0 adds up to the charge supplied by the source. At time 0, the charge supplied by the source is 0. So therefore, at when there is an initial charge in the capacitor, the charging starts at Q sub O and it increases until it approaches the steady state value. So having initial charge in the capacitor, the charging of the capacitor, the time that would require for the capacitor to be fully charged is shorter than when there is no charge stored in the capacitor. For the current is expressed as the rate of change of charge per unit time. So having the equation, the derived equation in from the preceding discussion, take the derivative of this equation with respect to time, and this would give us the equation for the current, which includes the current due to the initial charge. So this current E over R is due to the source E. So this current is due to Q sub O. So these two currents may add up or subtract depending on the connection of the capacitor in the circuit. If the capacitor has a positive polarity connected to the positive polarity of the supply, then they will oppose, and then therefore they will subtract with each other. If the positive terminal or the if the negative terminal of the charge of the capacitor, if the negative terminal of the capacitor connects to the positive terminal of the source, then the current will add up and they are aiding with each other. In case 1, if the charge stored in the capacitor is 0, then all the current will be coming from the supply E. And this is equals to E over R at time 0. This current decays as time approaches infinity. And at time 0, this current is E over R, which means that at time 0, current is E over R and capacitor is shorted. Consider that for series RC that the charge is 0. At time 0, charge is 0 and therefore current in the circuit at time 0 is E over R and the voltage across the capacitor is 0. This is can be represented with this circuit wherein as at time 0 the switch is closed and the voltage at the capacitor is 0 because the capacitor is short circuited and the current here is simply E over R. And as time elapsed, the I would decrease because capacitor charges up. And at time infinite, meaning steady state, at steady state condition, the current approaches to 0 and the capacitor opens, making the voltage across the capacitor equal to the supply voltage. If we are going to determine the voltage equation for the capacitor using this equation, Q over C, our Q is EC times quantity of 1 minus e to the negative t over RC plus Q sub O over e to the negative t RC. So divide this with C. Dividing this with capacitor, it would result to the voltage at the capacitor is equal to the voltage E times the quantity of 1 minus e to the negative TRC, meaning the curve approaches the value of E and adds up a voltage due to the charge Q sub O. However, if the charge Q sub O is 0, the voltage of the capacitor is simply due to the supply voltage. And at the start or at time 0, the voltage is 0 and approaches to the final value. While the voltage in R, which is equals to I times R, expressing the current in terms of E and in terms of its equation, we shall arrive at an equation that is consisting of E and the charge stored in the capacitor divided by the capacitance. So the voltage in R is affected by the charge stored in the capacitor, and it is in the form of decaying. If Q sub O is 0, then the voltage across the arc is simply coming from the supply voltage, and it is in decaying form. It decays to zero as the time approaches infinity, and the voltage in R approaches zero while the capacitor's voltage approaches it. So the voltage in R decreases while the voltage in the capacitor increases, approaching its final value. If we are going to plot the response of the voltages and current in the capacitor, let us consider first its response with Q sub O equals to 0. The current in the RC circuit starts at the E over R, and it decays to 0 as time elapses. While the voltage in the capacitor starts at 0 and increases to its final value as time elapses, which is equals to E. While this voltage in the capacitor increases, the voltage in the resistor decreases, approaching 0. If there is a charge stored in the capacitor, this is the current produced by the presence of charge in the capacitor, and it is at negative or below 0, under 0, and decays to 0 as time elapses. So the negative value must be placed below the 0 reference, and it decays. In case that the charge is a positive. However, if it is negative, then it adds up and it should be placed above the 0 reference. So here ends my discussion on series RC transient.